All right, so tonight we're going to be talking about ensemble learning, which is basically combining machine learning models to make a stronger central model. Because as we've seen already with decision trees, sometimes they can overfit, and sometimes just one isn't good enough. So we can actually create a bunch of them and combine them together using different methods. So those two methods are known as bagging and boosting. They're both pretty different in how they combine models together and also the use cases. So to start with, as I said, decision trees are prone to high variance and overfitting. We saw that in Monday's lesson. We were getting, perfect R-squared scores on our train set and then a lot lower on our test. But that's with just a decision tree by itself. So that's where bagging comes into play. So bagging is basically training a bunch of different models on different subsets of the features. So training this model on features 1, 2, 3, this model on features 3 through 5, just kind of randomly. And bagging helps to reduce variance and overfitting specifically. And how it happens is in parallel. So you kind of build all these models at once. You don't have to, build model 1, then build model 2. They can all be done kind of in unison. And then to bring them all together, all the predictions are just averaged. So if half the models predict, an output of 2 and half predict an output of 1, then we would end up putting 1.5 as like the final output of the bagging model. And then an example of a bagging model is random forest, which we'll go into now. Random forest is basically using a bunch of decision trees to make a stronger collective model. So you build a whole bunch of different decision trees using different subsets of the features, and then you combine all the predictions and take the average. And this is a really robust way to build a model. It really protects against overfitting and kind of helps to lower the variance of the final model. You'll see random forest used a ton. It has a lot of positives. It's really versatile too. One downside is that, like decision trees, random forest can only predict values that it was given. So for regression, it can only predict values that were in the training set. So you want to make sure your training set has the full range of values that you're going to end up predicting in the future. So this is kind of how it works. You have a whole bunch of decision trees here. They all make different predictions, and you kind of just add them all up and divide it up by however many you have. So in this case, most of them predicted 1. This would be for classification. So they predicted class 1. So in this case, the random forest model would output a prediction of 1.
What happens in a classification if you get equal? So say we had 8 models and 4 were 1 and 4 were 0.
That's a good question. I'm not sure if there's a default way to break the tie. I'd have to look at like sklearn in the library that has the random forest. They probably have a way to break it.
Maybe they always have an odd number of them, perhaps.
Yeah, that would probably be one way. They could also probably look at basically the accuracies of each of the models, and whichever group had the higher overall accuracy, maybe trust that one. Probably a couple different options. All right, so on the other side, boosting. Basically, you start with one model, you train it, and then you build a second model trying to compensate for the weaknesses of that first model. And you kind of do this iteratively. So instead of with bagging being kind of parallel all at the same time, boosting is sequential. So it has to go in an order. You start with the first model, and you keep building models that improve where the previous models have failed. And so boosting, conversely, it helps to reduce bias instead of variance, and it can actually increase the accuracy of a model. So bagging doesn't really help to make the model more accurate. It just kind of helps to reduce overfitting, whereas boosting can actually give you a higher accuracy or a better fit in the end. And so when it combines the models together, it actually uses a weighted majority. So each model is kind of given a weight depending on its accuracy, how well it does, and all those weights are then kind of added together, and the majority is the final prediction. And one example of a boosting method, there's quite a few, but this is kind of the first and like the classic one, is AdaBoost. And that's what we'll go into now. So AdaBoost basically does what I just described in boosting. It builds a bunch of baseline models, selects the best one, then it builds a new model, and it modifies the weights of where the first model messed up, so the classes or the samples that it misclassified, and it will try and improve based upon that. And like I said, the models are then weighted by their accuracy. So, you know, the ones that are better performing have a higher weight and they contribute more towards the final majority vote. And I have a diagram here that kind of explains how the AdaBoost works. So we're going to start in box 1 here. So this is us, we're fitting our first model. We're trying to separate the pluses from the minuses. So we draw this line here, and we were able to separate out 2 of the pluses here, but we see we have 3 pluses that we got wrong. So now the second model compensates for that by basically giving more weight and priority to those misclassified samples, and in this case it makes them bigger. And so now it's able to draw a line here, and it's able to correctly get all of the pluses in the blue box. But now it's also misclassified these minuses. So as we go into the third model, it will increase the size of those minuses that we got wrong before, and draw a new line. And this kind of keeps going on, and then basically all those lines are combined. And then in our final model, we have all of our classes separated out. So we have this blue region here, and then we have the red region for the minus. So even though each of these models by themselves didn't do the best job, together they ended up dividing and separating out our classes perfectly.
So is boxed for the result of these models, or is that like the fourth iterative?
So it's like the result. It's the combination of these models, because you can see each of their lines ended up in the final model. So like model 1 is really good about, you know, detecting pluses in this part of the data set. Model 2 can detect the minuses in this part of the data set, and so on and so forth. Yep. Alrighty. So you can then combine bagging and boosting models through another ensemble method, actually 2 of them. The first is a voting classifier. So you can take any number of models. They could be bagging models that are, you know, models that have been built from smaller models, or they could be boosting or a mixture of both. And you basically have each one cast a vote for whatever class you're trying to predict, and you basically take majority vote. In that case, as you mentioned, Andrew, like you probably want to have an odd number or have some way to split the tie. But so another way that is a little bit better and kind of avoids that is called a stacking classifier. So this basically fits, so the default is to use logistic regression, but it will fit a model using the predictions of each base model as the features. So it will kind of learn how to assign coefficients to each of the models and their predictions by seeing how well they do. And so it's kind of what's known as a meta classifier model, because it's trained on those base models, using them and their predictions as features. Do either of you have a Any questions on the stuff so far? Mostly makes sense without seeing it, at least.
Yeah.
As much as it could. Okay, so this stuff makes a lot more sense once you start using it and kind of see how these models work, how they improve things. So we're actually going to go into an activity now. This activity, you're going to take in a data set. It has, I think, like 5 features maybe. It's basically different environmental data points about a room. So it's like temperature, humidity, stuff like that. And then the target class, what you're trying to predict, is whether or not the room is occupied. So whether or not there's humans in it. Because basically, you know, humans change the temperature in a room, they can change the CO2 levels, that stuff. So without looking in a room, you'd be able to, from these sensors, detect if someone's in there. So your goal is to kind of go through all these different classification methods we've talked about and kind of compare them and see which one's going to be the best for whatever context you give it. So I have like 5 steps here. You're going to load in the data, scale it. Then you're going to do a train test split using this random state and test size. Then you're going to start at a baseline. You're just going to train a regular logistic regression model and a regular decision tree classifier and record the accuracy and F1 scores. And then you can answer this question here. And then after that, you'll try both a bagging and a boosting model, so random forest and ADA boost, and you'll see how those compare to your baseline models. Then you will actually use both a voting classifier and a stacking classifier to kind of combine all the models you built, and you'll see how those ensemble methods compare. And then lastly, you'll kind of just look at confusion matrices. Since it's classification, that can kind of tell us the most information. You know, do some models give more false positives than negatives? Are some better at recall or some better at precision? That kind of stuff. And then lastly, just to get you some practice making predictions on new data, I have a new reading here about a room. So I have all the data points there. Temperature, humidity, that stuff, and you basically have to plug that into your best model and make a prediction on whether or not somebody's in the room. So that's the activity. Do you guys have any questions before we begin?
No. Probably when we start working on it.
Alrighty.